asteroid. The DART mission is NASA's first test of a planetary defense technique called kinetic impactor, and it's going to smash itself into the moonlet Dimorphos, which orbits the asteroid Didymos, in order to change Dimorphos' orbit and show that we can deflect incoming asteroids if we need to. I lead the group of astronomers that are going to measure how much DART changed Dimorphos' orbit using ground-based telescopes all over the world. This is an animation. You can see Didymos and Dimorphos as one point of light. These curves show the brightness change due to Dimorphos moving in front of and behind Didymos. We can tell how quickly Dimorphos is moving around Didymos. We make these measurements before DART arrives, and then this is the same technique that we'll use after the impact to determine how much we've changed the orbit by. I make music. A lot of it, as you might imagine, has nothing to do with science, but a lot of it does. You know, I'm not immune to the charms of writing a gimmicky science song every once in a while. So I did write a song about DART.
The mission goes by the name of DART. That double asteroid redirection test, and just one flick should do the trick.
A lot of scientists definitely have a creative side. A lot of us write, a lot of us are in bands, or there's a lot who paint, and I think having that creative part of your brain definitely helps in science, just as much as it does in art.
Practice planetary defense with DART.
Hi everyone, I'm Josh Handel and I'm a Public Affairs Officer here at NASA. And I'm so excited to be joined today by Andy Rivkin, who you just had the opportunity to meet. Andy, thank you so much for joining us today.
It's a pleasure, Josh. Thanks for having me.
Of course. Andy's here to answer your questions about planetary defense at NASA and the DART mission. If you have a question you'd like to ask Andy about planetary defense or DART, send it in using the hashtag AskNASA or by writing in the comment box of wherever you're watching today's broadcast. So Andy, we just learned a little bit more about you from your video and your work with DART, but can you please tell us a bit more about why this mission is so important?
Sure, it's my pleasure. Asteroid impacts into Earth are one of the only, maybe the only, natural disaster that we can predict very far ahead of time and that we can also do something about. So there are a few different ways that people have come up with to address asteroid impacts and prevent them from happening. DART is a test of a technique called the kinetic impactor, where we basically take a spacecraft and we ram it into an asteroid. And by doing that, we change the orbit of the asteroid so that, in principle, if something were coming our way, we could move the orbit so that it was no longer coming our way.
Wow, that's a great answer. Thanks, Andy. And I actually see that we're already starting to get some questions in from our viewers. So we're going to go ahead and get started. And as a reminder, if you have a question for Andy, you can send it in using the hashtag AskNASA or by writing in the comment box of wherever you're watching today's broadcast. All right, Andy, are you ready?
I am. Let's go for it.
Our first question comes from Robert Clauderson on Facebook, who asks, will we be able to know what the composition of Dimorphos is by looking at the light from the impact of DART?
That's a great question. We have a pretty good idea of what the composition of Didymos is, the main body. Our theories of how asteroid moons form suggest that Dimorphos should be made of the same material. When the DART impact into Dimorphos occurs, we expect there to be a lot of debris that's thrown out into space by that impact. I don't think we're going to be able to directly measure the composition of that dust, but certainly we're going to try. And then the European Hera mission will be showing up a few years after the DART impact. And they will be able to directly measure the composition of Dimorphos. So they'll be able to confirm a lot of what we've been thinking.
So it sounds like we have an idea of what it's made of, but we won't really know until we get there. Is that correct?
Yeah, that's correct. We think that Didymos is made of the same kind of material as what we call ordinary chondrite meteorites. So they're very common material that falls to Earth. We think it's the same kind of composition that the asteroid Itokawa has, that the asteroid Eros has, and that the asteroid Apophis has. So it's a common material that is pretty commonly what falls to Earth.
Our next question comes from Indy Magoo on YouTube, who asks, would you try to find an object with a higher albedo so it would be easier to track?
So for those out there that are not familiar with what albedo is how reflective a surface is. So something like snow is very reflective, has a high albedo, as we say. Something like tar or a charcoal briquette has a very low albedo. It's very dark. As suggested, high albedo objects are more visible from far away. One of the things in asteroid science is we don't always get to pick what our targets are like. The targets pick that for themselves. So Didymos has an albedo we think of about 15 to 20%, so typical for rock. And Didymos has so many other great properties for carrying out DART that it's kind of, even regardless of albedo, it was clearly going to be the place to go.
Our next question comes from Vizwadeep Natarajan on YouTube, who asks, what are possible options to deflect a massive-sized asteroid?
That's a great question. The answer depends a lot on how much warning time we have before we have to deflect the asteroid, and the size of the object. So DART is part of kind of an overall national strategy for dealing with asteroid impacts. One of the other pieces is doing a search to find objects that are out there that might be hazardous and find them as soon as we can. The longer the warning time we have, the more different options we have. And some of the options might be, if an object is small enough that we just say, okay, it's going to burn up in the atmosphere, we're not going to worry about it. We'll just enjoy the meteor that it makes, and maybe pick up some little pieces if they make it to the ground.
So DART is obviously testing one form of asteroid deflection technology, but it sounds like a key point for it to work is that we would need to find a potential threat early. Is that correct?
Yes, that's kind of true for almost any of the techniques that people have considered. There are other techniques, including civil defense, which would in fact be go and wait it out in the basement. The most powerful tool we have in our toolbox is to use a nuclear device to detonate nearby a threatening asteroid, vaporize part of it, and deflect it that way. But we obviously want to have as many different tools in our toolbox as we can, because we're going to be faced with different scenarios, and so we want to make sure we have the right tool for the right job.
So kind of following up on how we're going to know DART will work, Videographer on YouTube asks, will we measure before and after impact, or will we only look at accelerations at the moment of impact? And how will we know these measurements how will these measurements be taken?
It's another great question. A lot of great questioners out there. From the Earth, Didymos and Dimorphos are going to appear as a single point of light. We're not going to see them separate. So what we can do, and what we will do, is measure the brightness of the system as Dimorphos goes around. And from the point of view of the Earth, Dimorphos will move in front of and behind Didymos, and that will make the brightness go up and down as it does that. We've been measuring that brightness for years. People have been measuring it in some form or another probably since 2003, but we've been measuring it for this project since 2015. So we know the period of that orbit very well. After the impact, we're going to keep measuring it. We're going to keep measuring the brightness of this point of light going up and down. We're going to measure the new frequency with which the brightness changes, compare that to the pre-impact measurements, and be able to say, okay, the orbit period was 11 hours and 55 minutes before the impact. Now it's 11 hours and 45 minutes or 38 minutes or whatever it is. That gives us the information we need to know how much we changed the orbit.
Our next question comes from Alan Ranke on Facebook, who asks, what are the characteristics of the spacecraft itself?
The spacecraft is about the size of a vending machine, not counting the solar panels. So it's 2 meters by 2 meters by 2.5 meters, something like that, but a vending machine. The solar panels, which you can see in the video here, are rollout solar panels. That's one of the new technologies that's being tested out on DART. When those are fully deployed, then those are 18 meters from tip to tip, which is a little bigger than kind of the length of a typical bus. So we're going to take this spacecraft. It's several hundred kilograms in mass, I think 500 or 600 kilograms in mass, and it is going to impact Dimorphos. Dimorphos is about the size of one of the pyramids of Egypt, and it's going to impact it at something like 6.5 kilometers a second. In imperial units, if you prefer, that's something like 4 miles a second. So basically, we're firing this vending machine at one of the pyramids of Egypt very, very fast.
So kind of following up on that, how is it possible that something so small, you're saying the size of a vending machine, impacting a pyramid essentially in size, how can something so small change something so big? How can that motion and change, how can that change in space be altered?
That's part of the reason, these objects move through space something like 30 kilometers a second, so 20 miles a second. If you have enough warning time, if you have 20 years of warning, 30 years of warning, 15 years of warning, all you need to do is change that speed by a little bit, just a fraction of an inch per second, and that gives it enough time to miss the Earth entirely. It's sort of like, if you can imagine, if you had two trains that you knew were going to collide, if you knew it a day before, then one of the trains would only have to change its speed by a little bit and you'd be fine. If you found out 5 minutes before, then it's a very different story. If you found out 10 seconds before, then you really have to take some drastic action. So part of it is the key is finding them early so that you can just make a little change and not have to do anything too drastic.
Logan on YouTube asks, how long have you been working on DART?
I've been working on DART since very close to the beginning. I think it's a little over 10 years since, it basically was a two-page document that my colleague Andy Cheng over also at APL had come up with the idea of testing this technique on a binary system, the DA, double asteroid, part of DART. And from there, it's been kind of taking that two-page document and making it more and more, sure, more and more mature, so we could bring it to NASA, convince them that this was a good thing to do. And then, of course, the engineers doing all of their work with the hardware, putting it together, building it. That's been the last few years. So it's really, really amazing that now we're seeing this thing that started out as, again, this kind of two-page document turn into a piece of hardware that's going to sit on top of a rocket and then make its way out to the asteroids.
So Andy, I noticed that you said, the double asteroid part of DART, double asteroid redirection test, that we're going to this binary asteroid system. Can you tell me a bit about why that's important? Absolutely.
The idea of testing a kinetic impactor like DART predates DART by quite a bit. The European Space Agency was first looking into it in the early years of this century, but when they conceived of it, they imagined visiting a single asteroid and changing its orbit around the sun. So doing that, as you might imagine, is a very precise measurement that needs to be made, and their concept had a second spacecraft sitting there to make that measurement. That was more spacecraft than the Europeans wanted to devote to the problem at the time. So the idea of going to a double asteroid and watching the brightness go up and down from the Earth means that you can do it with just one spacecraft. You don't have to build two spacecraft, send two spacecraft. You can change the orbit of the moon and then measure what you did from telescopes on the Earth.
So keeping in line with DART and the launch, so Melanie on YouTube asks, I'm excited and I'm scared. What should I expect on the 23rd, 24th of November?
Well, Melanie, I feel you. Excited and scared is, I think that's going around. So we're going to be launching out of Vandenberg Space Force Base, and we're going to be on a Falcon 9 rocket. We are going to launch. It's going to be kind of late at night, something like 10:20 p.m. on the West Coast, and in the early morning Wednesday on the East Coast is the plan. And then you can see the video here. DART will separate from the main booster. It's going to spend a little time getting its solar panels extended. And then we think about a half hour, 20 minutes to a half hour after the launch, it will fire the rockets to kind of get on its way toward Didymos. So we're looking forward to it, and we're excited. I think it's a crazy thing we're doing. So I think scared is not a foreign feeling, but also we're all feeling very confident.
As a reminder, we're chatting with Andy Rivkin from NASA's Double Asteroid Redirection Test Mission. And if you'd like to ask him a question about planetary defense at NASA or the DART mission, you can send it in using the hashtag AskNASA or by writing in the comment box wherever you're watching today's broadcast. So Andy, our next question comes from Patricia Benner-Smith on Facebook, who asks, so will pieces of the asteroid break off, and will they become millions of little meteorites that might hit our satellites or even our planet?
Great question, and something that is something that we've looked into and others have looked into. The expectation certainly is that when DART hits Dimorphos, that it will make debris. That debris will come off of the surface of Dimorphos. And in fact, LICHA-CUBE, which is a CubeSat that the Italian Space Agency is building, has built. It's already built. It's done. It's attached. LICHA-CUBE has for its objectives to actually take images of the debris cloud that DART makes when it impacts, because that's going to give us information about Dimorphos itself. The amount of material that is made by the DART impact is not very large. You might remember that objects are naturally hitting objects in space all the time and making meteorites. People have studied how much material from the DART impact might make its way to Earth, and the amount is minuscule. I think the report I remember seeing was maybe one extra shooting star over the course of a decade. So we are not going to do anything that's going to come to Earth. We're not going to do anything that's going to be a problem for satellites or anything like that.
So speaking of LICHA-CUBE, Dan Shields on Twitter asks, once hashtag DART mission and LICHA-CUBE results are analyzed, what's next? Are there subsequent missions or targets identified, or will that come later?
Sure, I'm always happy to answer, a Twitter question with my tweets. The most direct, immediate follow-up to DART is the Hera mission, which the European Space Agency is going to be launching a few years after DART. It will arrive at the Didymos system. I should know this. I think it's 2026. And they will do direct measurements that will be useful on their own. They'll do some great science, and they'll also be doing some follow-up measurements that will help us continue to analyze DART. In terms of the Planetary Defense Office, the next mission that I think most people are expecting is a telescope mission called NEO Surveyor, which will go back to the job of trying to find asteroids out there, trying to catalog the asteroid population and understand the potentially hazard asteroids that are out there, make sure that nothing is coming our way.
So Jamie Jeans on Facebook asks, is there an asteroid coming our way? Is there an asteroid headed toward Earth?
No, but I'll say no asterisk. We are hit by material all of the time. Anytime you go out into your backyard and you see a shooting star, that is asteroidal or cometary material hitting the Earth. It's maybe the size of a sand grain. The Earth gets hit by objects the size of the chair I'm sitting in. I don't know the chair you're sitting in. I assume it's probably about the same size. Maybe 3 or 4 times a year. Depending on the size of your couch, we get hit by couch-sized material, again, maybe once a year. As you get larger and larger, objects, they hit less and less frequently. That's again part of the reason that we want to send missions like the NEO Surveyor out to look for material objects that might be large enough to worry about coming our way. We know of no objects that are large enough to cause any damage that are coming our way. So I can absolutely reassure you of that.
Well, that's good to hear. Our next question comes from Sarah on Twitter, who asks, how long will it take DART to get to the Didymos system?
Great question. DART will arrive in the end of September to the start of October in 2022. The exact date of arrival depends on the exact date of launch, but it's going to be somewhere in that last week of September to the first couple days of October. Our launch period is a long one, so a week from tomorrow is the first opportunity we have to launch. Yeah, that's crazy. But the last opportunity we have to launch is a few months from now. Certainly the expectation is we'll launch as soon as we can. But if for some reason we didn't launch until January, we still would arrive kind of in that late September, early October timeframe.
KCT Monday on Facebook asks, can you predict the new trajectory upon the collision of DART?
The trajectory of Dimorphos is the new trajectory of Dimorphos. The new orbit of Dimorphos is what we're hoping to measure. Given the amount of momentum we think we're bringing in, or we're sure we're bringing in, and given the way we think Dimorphos will act when we hit it and the amount of material we think it throws off, we're expecting to change the orbit period by something like 10 minutes. But it could be 20 or it could be 30. We don't think it could be much less than 10 minutes. We are not, and we're going to make it into a smaller orbit as shown in this animation here. So we know we're going to make the orbit of Dimorphos a little bit smaller. We don't think we're going to appreciably change the orbit of Didymos around the sun. In fact, I say we don't think. We are confident we're not going to change that. In fact, we're not going to make a change that is measurable compared to our current knowledge of the orbit of Didymos around the sun. So the system around the sun, we're really not going to change.
And speaking of this asteroid system and DART's kinetic impact, Robert Ciarantini on Facebook asks, why not test our theory on an asteroid that does not pose a threat so that we can measure that reaction? And I think, Andy, you might have some clarifying information here.
Yeah, absolutely. Didymos is not a threat. Didymos is not, the orbit of Didymos does not intersect that of Earth. We're not going to change it to do that. Part of the confusion, or there's the potential for confusion in that there is a grouping of asteroids that are called potentially hazardous asteroids, and they are defined by their orbits. But even though they are all called potentially hazardous asteroids, they're not actually potentially hazardous in the way that most people would use the term. So Didymos' orbit comes close to Earth, but not close enough that it is actually going to be a threat to Earth, no matter what we do to it.
Interesting on YouTube asks, will NASA be able to control DART's trajectory, or is it entirely reliant on SmartNav?
SmartNav is our automatic navigation system that will bring us in for the kind of final approach. It is not going to be operating until the last few hours of the mission. Up until then, there will be trajectory changes and burns that are typical for a mission. My understanding, and I'm not an engineer, so hopefully I'm not going to screw this up. My understanding is that there is the potential to possibly intervene, but that there is no plan to intervene. So we think SmartNav is going to be able to do the job in those last few hours, and we'll do just fine.
Ivu0404 on YouTube asks, will the loss of the crashing asteroid affect the trajectory of the other asteroid?
Oh yeah, we are not going to destroy the Dimorphos. It's going to we're going to make a crater. We think the crater will be something like 15 meters across, but the whole object is 160 or more meters across, and it's that distance deep too. So again, we're hitting one of the pyramids with a vending machine, and kind of no matter how hard we throw the vending machine at the pyramids, we're not going to do more than maybe make a mess of the surface. So Dimorphos will be fine. Dimorphos has had worse, and may again have worse after us. So it'll be okay.
So Andrew, we have time for one more question, and I hope you could tell us a bit more about your career. Your job at APL sounds fascinating. I'm curious if you could just tell us a bit more about how you got to where you are now, and perhaps if you have any advice for those watching today.
Sure, free advice worth every penny, as they say. I started out, I've always loved space. Ever since I was a kid, one of my first memories was the Viking landing on Mars. I was 6 or 7 years old, and I remember seeing the newspapers and getting into space then. And I've been following it avidly since. I went to undergraduate at MIT, where I majored in Earth, Atmospheric, and Planetary Sciences. I knew even then that I was a planet guy and an asteroid guy, not a galaxy and cosmology kind of guy. Went to graduate school in Tucson at the University of Arizona, where I met a bunch of great folks. I met some great folks at MIT too. And then I eventually made my way back to MIT as a research scientist, and from there I've been at APL since 2005. So advice I would give anyone who's in science is to keep your non-science hobbies. They keep you fresh. They allow you to kind of stretch your mind in ways that maybe you don't necessarily always get kind of hunched over your Python code or your telescope. So just hold on if you can to your dancing or your violin playing or your sketching or your craft, your candle making. So that would be my advice.
Andy, thank you so much again for your time and for joining us today. It's really been a pleasure.
Thanks again for having me. Thanks for all the great questions, and go Dart.
Go Dart. And thank you all for watching from home. You can keep up with NASA's DART mission on social media by using the hashtag DARTmission. And you can follow NASA's solar system on Twitter, Facebook, and Instagram. You can keep up with all of NASA's asteroid-related and planetary defense-related news by following Asteroid Watch on Twitter. And for all of the latest news on DART, visit nasa.gov/DART. Finally, be sure to watch DART's launch, currently scheduled for November 24th at 1:20 a.m. Eastern Time. Thank you all again for joining us today, and keep looking up.